Hello everyone and welcome to this webinar dedicated to the new vibration analysis in SCIA Engineer 25. So we'll have a look at an analysis of a steel footbridge accounting for vibrations. So of course during the webinar, do not hesitate to ask your questions in the dedicated area and we'll have some time at the end to look at them and try to answer them. With regards to the agenda, we'll start with a small theoretical background. We'll look at some guidelines to ensure pedestrian comfort, safety, and structural durability. And then we'll delve into modal analysis, where we'll have a look at the eigenmodes and their corresponding frequencies and shapes. And then we'll have an overview of the new possibilities in SCIA Engineer 25 with regards to the creation of harmonic loads, which we will then apply in the model in itself to do the analysis of the footbridge, of course. And then we'll get the chance to see the overview of the new detailed dynamic results. So of course, it will help us understand how the structure behaves under such loading. And we'll have a look at some suggestions for the improvement of the structure to make it more optimized. So let's start with the theoretical background. So we will use the guidelines from SETRA, which are the assessment of vibrational behavior of footbridges under pedestrian loading. So these guidelines are there to ensure pedestrian comfort, safety, and structural durability. So what does this guideline tell us? The first thing is about the methodology chosen to decide if a vibration analysis is needed or not. So basically, the owner does an assessment of the traffic and decides on a comfort level needed. So in terms of traffic, we have 4 different classes, which we'll look more into detail later on. For class 4, no calculation is required. If the footbridge is from class 1 to 3, we will need to do a calculation of natural frequencies, and this will tell us if we have a risk of resonance or not. So if the structure is sensitive to resonance, the accelerations of the structure are calculated through a vibration analysis. So this vibration analysis will give us the acceleration limits, and these accelerations will tell us what kind of comfort do we get. So in terms of classification of footbridges, the class 1 corresponds to an urban footbridge linking up high pedestrian density areas, so it's subjected to very heavy traffic, whereas class 2 corresponds to an urban footbridge linking up populated areas subjected to heavy traffic. And for class 3, it's a footbridge for standard use that may occasionally be crossed by a large group of people. And for class 4, it's a seldom used bridge, which is built to link sparsely populated areas. So this is why we don't really do any risk control on it. As for the comfort levels, we have 3 categories. For the maximum one, the accelerations undergone by the structure are practically imperceptible to the users. Whereas if you want an average comfort level, the accelerations will be merely perceptible to the users. And for the minimum level, under loading configurations that seldom occur, accelerations undergone by the structure are perceived by the users but do not become intolerable. And of course, we have a 4th class, which would be the class where the comfort level is not satisfied at all. So the accelerations are classified in different ranges. So the level of comfort is assessed through reference to the acceleration undergone by the structure. These accelerations will, of course, be calculated using different dynamic load cases. And as you can see on the left side in this table, there are 4 ranges of values for vertical and horizontal accelerations, respectively. So for example, for the maximum comfort, it will correspond to a range between 0 and 0.5 meters per square seconds for the vertical vibrations. And then, with regards to the risk of resonance, it is assessed through reference to the natural frequencies of the structure. These natural frequencies are calculated using specific combinations of mass groups that we will create in SCIA Engineer. And as for the comfort levels, we have different ranges. There are 4 for vertical and horizontal frequencies, respectively. So the most dangerous range would be between 1.7 and 2.1 Hertz for vertical loads, for example. So the last step here would be to specify what type of load cases do we need to create in our model? So the analysis to be carried out will depend on the footbridge class and on the range within which its natural frequencies are situated. So there are three load cases that are identified based on these criteria. For example, if we have a class 2 footbridge and we fall into the frequency range, which is of type 2, we will create a case 1 load case. So in our example that we will show later on, we will use a case 1 load case. And once we establish that, we will need to determine the density of the crowd. If it's class 1, we have 1 pedestrian per square meter. If it's class 2, we have 0.8 pedestrians per square meter, and this value falls to 0.5 if we are of class 3. And of course, not all the pedestrians will walk at the same pace and would be in phase. So first we establish the real number of pedestrians involved, which is the surface of the footbridge multiplied by the density of the crowd. But then we would need to calculate an equivalent number of pedestrians, which is calculated based on the formula you can see on the screen, 10.8 multiplied by the epsilon n, which is square root of epsilon multiplied by n. And another factor which we need to consider is factor psi, which takes into account the frequency that we are considering. So if we fall in the range 1, between 1.7 and 2.1 hertz for vertical loads, we would be having a value psi equal 1. If the value of the frequency is below 1 or above 2.6, this psi factor will be nil and no analysis will be required. And if we are in the intermediate ranges, this value will be calculated through an interpolation. And we have some values for the load to be applied if it is vertical, longitudinal, or transversal, as you can see in the table on the left side. So now, in terms of modal analysis, which will give us the eigenmodes with their corresponding frequencies at shapes, we will create the example of the CETRA guideline, which is from the appendix. It's example 5.1.1, which corresponds to a Warren type lateral beam footbridge. Here we have a footbridge of 38.85 meters with a width of 2.9, but a really useful width of 2.5 meters. So this bridge was modeled in 3D in SCIA Engineer, and the model analysis was carried out. We'll have a look at it in just a second in SCIA Engineer directly. And the natural frequencies which we calculated are very similar to the ones calculated in the guideline. So the first thing to establish here is to specify the loads to be applied, which will be corresponding to the presence of pedestrians. First, we will assume that the footbridge is of class 3, so we will consider 0.5 pedestrians per square meter. So the number of pedestrians can then be calculated as 48.6. We assume a mass of 70 kilograms per pedestrian, which leads us to a total weight of 3,402 kilograms and an equivalent surface load to be applied in SCIA Engineer of 35 kilograms per square meter. So now let's go directly to SCIA Engineer to see this example. So you have a model which has, of course, 1D members, which have steel cross sections, and the 2D shells here, which are made of concrete. And so the first thing to be done is to create the load case corresponding to the pedestrians. It's a live load, and you can see that we have applied a load of 35 kilograms per square meter in that case. The next step would be to calculate the masses corresponding to this. So of course, in SCIA Engineer, you have the mass groups. We have a first group associated to the self-weight in itself, and the second group, MG2, associated to the loads of the pedestrians. Then we create combinations of mass groups. The first combination will only include the mass related to the self-weight, and the second combination will have the mass related to self-weight plus the mass related to the presence of pedestrians. Then a modal analysis was carried out with 10 eigenmodes, and we can have a look at the results and the calculation protocol. We will be able to see for the first combination, the total mass and the moving mass. And if we look at the table of the eigenmodes, you can see that the first one appears at a frequency of 2.16, and it has an 81% mass participation in the Z direction, so in the vertical direction. If you look at the second mode, it has 39% mass participation in the Y direction, but its frequency of 3.38 is very high and it falls outside the range of critical frequencies for horizontal loading. So the only direction that we will consider in this example will be the vertical one. And if we try to find a second mode which acts in the vertical direction, it will be mode number 9, which has a frequency of 10.86. Again, this falls in a range which is outside the critical range, so we will only consider the first mode. So the same thing goes for the real combinations that we will consider, which also takes into account the mass of the pedestrians. In this case, the first mode is still the most important one in direction Z, with 81% of mass participation, and its frequency is a bit lower, it's 2.08 in that case. And for mode 9, we still have a participation in Z, and the frequency is high, it's 10.7 approximately. So again, we will only consider the first frequency. The second thing that we can see here is the displacement. So if you go to the 3D displacements and we consider the first eigenmode, which has a frequency of 2.08, if you look at the results, you see that it's purely a vertical displacement, and we understand its importance in that case. If you look at the second eigenmode, in that case, of course, displacements acts more in the Y direction, as you can see. This confirms the mass participation found in the table. And for mode 9, which acts vertically, you can see that it's also vertically, and the shape is a bit different than the first mode. But yeah, again, this mode will not be considered in the vibration analysis later on. So now let's go back to the presentation, and now we will delve into the new possibilities in SCIA Engineer 25 with regards to harmonic loads. First, we need to establish what kind of functionalities are available in the different modules of SCIA Engineer. As you know, SCIA has different modules which have some functionalities included in them, and these modules can be available in different editions of the software. So in the module seismic and harmonic analysis, you have access to a harmonic analysis with a single frequency. You will also be available to ask the dynamic results in terms of acceleration, velocity, and displacement, and you can ask for a detailed model table. So this was available in the old versions of SCIA Engineer only in the old interface. Now it's available also since SCIA 25 in the new interface. But if you need to access the new functionalities, they are available in the vibration analysis module, which is included in the Ultimate Edition of SCIA Engineer. This will include the harmonic analysis using a frequency range. You will have out-of-phase harmonic loads. You can also apply harmonic loads, which are line and surface loads. You get access to RMS results and the sign of harmonic loads based on an eigenshape. So let's start by discussing the different types of loads. So point loads are available in seismic and harmonic analysis module, and it includes point loads in a node, on a 1D member, and free point loads. Whereas line loads and surface loads are only available if we have the vibration analysis module. And for line loads, they can be applied on 1D members, on 2D edges, and they will be also available as free line loads. Whereas for surface loads, you can use surface loads on 2D and also free surface loads. Another new functionality is the possibility to specify the period division for summation. So you have a list of different values. It goes from 6 to 360. If we choose the option 360 subdivisions, this will give the most precise results, but it can lead to slower output of these results. Whereas if you choose a period division of 48 or 72, for example, the results will be very close to the option with 360 divisions, and of course, that will be faster. If you choose period division equals 6, this will give very fast results, but they are less precise than the other options. As you can see here in the different graphics, you can see that the shape of the sinusoidal uh, diagram here is kept if you have 360 or 48 subdivisions, but if you have 6, it will be more an interpretation of different lines, and it will not be precise enough in all cases. So we recommend to use 48 or 72 divisions in general. The second new option is the possibility to sign the loads, the harmonic loads, of course, based on the eigenshape of a certain mode. And this is available for 1D and for 2D members. For example, if you look at the beam on the left side, you can see that an eigenshape gives a displacement downwards on the left side and upwards on the right side. What can be done now is, instead of applying two different loads, one which be downwards on the left side and upwards on the right side to simulate the correct behavior, you can apply a single load on the whole beam and specify the eigenshape. So in this case, the eigenshape represented on the top as your shape that will sign your load. So in the background, SCIA Engineer will adapt the sign of the load along the beam or along the surface, and the analysis will be carried out in a correct manner. We'll have a chance to see that in an example in the footbridge that we are evaluating today. Next, we will talk a bit about damping. So before we had the possibility to have a constant damping in SCIA, now we introduced also the option to use a Rayleigh damping. For constant damping, the dimensionless damping ratio is defined in percentage. As for the Rayleigh damping, it is defined as two frequencies at specific, as two values at two specific frequencies, and the coefficients alpha and beta will be calculated automatically. So as you can see on the graphic on the left side, here we have a value of 3% for damping at a frequency of 1 and 10 Hertz. This will allow SCIA to calculate coefficients alpha and beta, which are used in the formula to calculate the variation of the damping along the different values of frequencies. It is represented here by the green diagram in our picture. So then we will talk a bit about the harmonic methods which are available. So now we have the choice between a full harmonic or a modal superposition method for the modal analysis, for the vibration analysis, sorry. But for example, for the full harmonic method, it is only available with the Rayleigh damping and does not require a prior modal analysis. Whereas the modal superposition method, it uses factored mode shapes to be summed and to calculate the harmonic response. So of course, it requires a prior modal analysis. And the modal superposition method provides positive and negative values of the response amplitude, while the full harmonic method provides absolute values only. So for example, on the beam shown in here, on the left side, you can see the moment distribution for a modal superposition method. So you can see that negative moments appear on the supports, whereas for the full harmonic method, only positive values are shown everywhere. Another new possibility is to create a harmonic load case with a range of frequencies. When we do that, a set of load cases are generated based on the minimum and maximum frequencies that we specify and the step that we introduced. For example, here you can see an image where the minimum frequency is 50, the maximum one is 100 Hertz, and we have a step of 1 Hertz. So it will create 51 load cases going from 50 to 100 Hertz with a step of 1. So this allows us to have a fast overview of the response of the structure under different frequencies. It lets us create this load case faster and group them in a certain class later on to have an overview of the results. The last new option here is a possibility to have out-of-phase harmonic loads. So it is now possible to define a phase angle for each load in a given harmonic load case. This means that all the loads will have the same frequency, but they will not be synchronized. So again, we're talking here about a single load case. So this is why all loads will have the same frequency, but inside this load case, all the loads will not really have the same phase angle. So if you look at the graphic on the left side, you can see here two representations of a harmonic response. You can see that the red one has a phase angle with regards to the blue one. So at t equals 0, the blue one is at a amplitude which is equal to 0, but the amplitude which is equal to 0 for the second response starts a bit later. So this will be identified in terms of degrees in SCIA Engineer. So for example, we can introduce three different surface loads in our beam in here. So the first load is applied with a phase angle of 0 degrees. This means that at t equals 0 seconds, the intensity is nil. Whereas if you apply a phase angle of 45 degrees, it means that the intensity of the load will be nil at a position which corresponds to the eighth of a period. Whereas if we choose a value of 90 degrees for phase angle, it means that the intensity will be nil at the position which corresponds to a quarter of a period in that case. Okay, so these load cases will now be applied in an example on the footbridge that we have shown earlier. So first, we will need to define in which load case do we fall. We have seen earlier that the natural frequency of the first eigenmode, which is in a vertical direction, is 2.08 Hz, which places it in a range 1 of vertical frequencies. So the analysis corresponds to a case 1 situation, and we have a value of psi equal 1 since it's in a range 1 of frequencies. So the load will be calculated using the formula on the left side. So we see the equivalent number of pedestrians, and it leads to a harmonic load, which we would have as a surface load of 1.68 kilograms per square meter or 16.8 Newton per square meter. So now we will go back to SCIA to see that directly in the model. So we have created a new load case at 2.08 Hertz. So basically, you define the load case as being of dynamic type, then the specification is harmonic. And in our example, we chose the modal superposition method. And the damping is constant with a value of 0.6% as mentioned in the technical guideline. We have chosen a number of subdivision of 72, and the frequency is of 2.08. So for now, we don't do any load signature in this case. And of course, the mass combination used is CM2, which takes into account the self-weight and also the effect of the presence of pedestrians. So after establishing our load case, we run an analysis, and then we will have access to some results like the 3D deformations, of course. So if you look at the 3D deformations under the load case of the pedestrians without any harmonic analysis, you would have, sorry, it's class 3 in that case, you would have a displacement of 5.6 millimeters. When we look at the results for the load case, which has a frequency of 2.08, now the displacement is of 18.2 millimeters. It's much bigger, so this is because we have applied the load at the resonance level, so it gives very big results in terms of displacements. As a second thing that we can look at in that case is also this displacement for a combination, which would include this load case. Let me explain myself in here. If you go into combinations, you can create an envelope of type serviceability, which would include this load case on its own. Here you can see that it's multiplied by 1. But if we go into the nodal displacements, let me choose this node. If I ask for the vertical displacement for the load case in itself, it would give us the 17.8 millimeters we've seen earlier. But if I ask it for this combination we have just created, we will have both negative and positive values. Because of course it's a vibration, so the amplitude can be the same upwards and downwards. And if we ask for a preview, you can see that the first value of minus 17.8 is obtained for combination number 1, which is minus the load case we have. And the value of 17.8 is obtained for the load case in itself multiplied by 1. So this means that we can cover both amplitudes using a combination which will, in the background, multiply our load by -1. And then what we can do is also create another type of load case, which will be with a range harmonic load. So here I've created the same load case, but the thing I have changed is that I chose a specification of harmonic range instead of harmonic. And I chose a minimum frequency of 1, a maximum one of 5, and a step of 1 Hertz. So what SCIA does in the background, it creates 5 load cases at 1, 2, 3, 4, and 5 Hertz. So now I can go again into the displacements and I can see what happens, for example, at a frequency of 1 Hertz. In that case, we have 0.3 millimeters. At 2 Hertz, it will be a bit bigger, 3.2. Then at 3, it comes down again at 0.2, and it falls also at 4 Hertz because we are going into ranges which are not anymore in the critical ranges of frequencies, so the value becomes smaller. And another possibility in this case is to create a class of results which will include these 5 load cases together. So now, if I ask the results for this harmonic load case, harmonic class, sorry, if I ask for extreme no, graphically it will show me the biggest and smallest values. And in the preview, we will have the value for each of the 5 load cases. So we see the value at 1, 2, 3, 4, and 5 Hertz. And you can notice that at 2 Hertz, we have the biggest value. So then let's go back to the presentation and we will talk about the new detailed dynamic results which are available in SCIA Engineer 25. So in this version of SCIA, you can get detailed results for a modal analysis eigenshape and for a seismic or harmonic load case. For harmonic load cases specifically, it is possible to get the displacements, the velocities, and the accelerations on the nodes. So these results can be obtained on regular nodes, and they can also be obtained on FEM nodes. And we can ask for RMS values instead of peak values. So the RMS values are indeed the peak values multiplied by square root of 2 and divided by 2, which give us a sort of a mean value because obviously the load will not be at its peak at every moment because we have a sinusoidal shape of intensity of the load. So this will give us a overview of how the structure will behave in a mean way instead of at peak values. So now I will go back to SCIA to show you these new types of results. They are available in the results menu. And if you look at dynamics detailed. So here, let's start with our first load case at 2.08 Hertz. We can ask for displacements as usual. It will be in the 3 directions and we also have access to the rotations. So if I ask for UZ, you can see the 17.8 millimeters that we saw earlier. We can ask for velocities, which is 0.23 meters per second in the vertical direction, and for accelerations, which is the most important value here. And we notice that we have a value of 3.04 meters per square second in that case. We will see that later on in the summary, but this value falls outside the limits of the comfort level, so we need to think about optimizing our structure in that case. Another thing that I have done in this model is that I have considered 2 other classes. So I took the hypothesis that we are of a class 2 footbridge and a class 1 footbridge. For the class 2, we assume that we have 0.8 pedestrians per square meter, which is equivalent to a surface load of 56 kilograms per square meter. For the one of class 1, we assume 1 pedestrian per square meter, so it's 70 kilograms per square meter. So obviously for these 2 load cases, we have created the associated mass groups, mg3 for class 2, mg4 for class 1. We have also created the appropriate combination of mass groups, CM3 and CM4 respectively. So if you go again into the calculation protocol and have a look at the natural frequencies, we can see below the tables for CM3 and CM4. For the class 2, we see that the frequency is now 2.03 for the first eigenmode, and the participation is still of 81% in the vertical direction. And for the class 1 footbridge, the frequency falls to 2 Hz, and we have a mass participation of 81%. So for these two types, we are still in the range 1 of natural frequencies. And for class 2 footbridge, it corresponds to a case 1 load case. And for the class 1 footbridge, it corresponds to a class 2 in type 2 load case. So we will need to carry out the vibration analysis. So we have identified the loads to be applied. So for load case, which is associated to class 2, we use a frequency of 2.003 Hertz. And of course, we need to use combination of mass groups, CM3 in that case. For footbridge of class 1, we use a frequency of 2 Hertz, and the frequency, and the combination of mass groups is combination CM4. In terms of loads themselves, for the class 2 footbridge, we have a load of 2.13 kilograms per square meter to be applied, and for class 1, it's 5.26. So if you look now at the detailed results, we can see the acceleration for class 2, which should be 3.92, and for class 1, it will be even bigger, it's 9.42. So of course, for both cases, we fall outside the limits of the comfort level required. So now I will show you also another option is to show the results on a beam with the results on FEM nodes. So as you can see now, it depends on how we divide our beams in the solver and how many subdivisions we divide it. So we will have a value of acceleration or displacement or velocity on each FEM node along the member. And it can also be obtained on a surface element, as you can see in here. So then we will do an overview of the results of the 3 classes of footbridges. So for the 3 of them, the frequencies are in the range 1 of frequency. The load cases to be used are either load case 1 or 2. And the accelerations calculated are all above the limit acceptable, so the comfort level is not satisfied. So the structure needs to be adapted. So here are some suggestions for the improvement of the structure, which were based on the technical guideline. The first thing that we can do is to increase the thickness of the sheet metal from 12 to 14 millimeters, and we increase the depth between the members to 1.415 meters. So now, in our example, for the class 3 footbridge, the frequency will fall outside the range 1, and in that case, we don't really need to do any analysis anymore because we will fall outside this limit. As for a class 2 footbridge, for example, we will get a frequency of 2.41 Hertz, and it is then situated in a range 2, and it is analyzed as a case 1 situation. So we calculate then the coefficient psi because the value of frequency is above 2.1, and we get a value of 0.21, which will allow us to reduce the surface load to be applied in our harmonic load case. And then the new load to be applied is of 3.4 Newton per square meter, and we will look at that directly in SCIA Engineer. So I will open the model of the modified footbridge. So we have also created the load case for class 3, 2, and 1, as usual. And so for class 3, if you look at the calculation protocol for combination CM2, we can see that the frequency is of 2.46, so we are in range 2. And since we are of class 3, we don't really need to do any vibration analysis. For class 2, it's 2.41 Hertz, so we need to do the analysis. And again, for class 1, it's 2.37, and we fall in a range 2, but we still need to do the analysis. So the loads to be applied for class 2 are 0.35 kilograms per square meter. And for class 1, it's 1.1 kilograms per square meter. If we look now at the results in terms of accelerations, for class 2, we will get a maximum acceleration of 0.57 meter per square seconds, which falls in the mean comfort level. And if we look at class 1, we will get an acceleration of 1.85, which is a minimum level of comfort. So, in summary, for class 3, the vibration analysis is not needed anymore. For class 2, we have a mean comfort level, and for class 1, we have a minimum comfort level. But we can still apply some improvements on our model. So according to the guideline, we can see that we can increase the thickness of the sheet metal to 16 millimeters. So now the natural frequencies will be greater than 2.6 hertz, and the coefficient psi will be equal to 0, and the analysis will not be necessary for class 2 anymore. And for class 1, we will fall into the load case 3, which would need us to use the second eigenmode. But as we have seen earlier, the second eigenmode in the vertical direction has a very high frequency. So in that case, we can also consider that the analysis can be neglected. So this was what I wanted to present today. Let me check if you have some questions. Indeed, there are already some questions. So with regards to the Rayleigh damping or the constant damping, this will depend also, of course, on the type of structure and on the technical guidelines that you are following. So for example, here, according to the CETRA guideline, for a mixed footbridge like this one, we can assume, it is possible to assume a constant damping of 0.6 hertz. For other types of structures, because of course the harmonic analysis is not really only for footbridges, it can be used for machines acting on certain floors, etc. In that case, it can be that the damping will not be constant along the ranges of frequencies, and that in that case, you can use the Rayleigh damping. So thank you everyone for your attention, and have a nice day, and maybe we'll see each other again in future webinars. Bye bye everyone.